it is the Sattagiri College of Engineering also as a HOD and professor. Now Gayatri will introduce our chief guest for this presentation.
So very good morning one and all. On behalf of President of Children's Education Society and Chairman of Oxford Education Institution, management, principal, deans, HOD and staff and students of the Oxford College of Engineering, I, Gayatri, student of 3rd semester, Degree Department. It's my great pleasure in welcoming you all for today's guest lecture on pollution performance on insulator organized by the Degree Department. On this occasion, it's my great pleasure and honor to welcome our chief guest, Dr. K. Ravi, to this event to share his immense knowledge and experience. It's my great privilege to welcome our chairman, Dr. S.N. B.L. Narasimha Raju Garu, Principal Dr. N. Kannan, deans, heads of the department, and staffs to the guest lecture. Dr. K. Ravi completed his graduation in electrical engineering from Bangalore University and post-graduation in high voltage engineering from Indian Institute of Science during 1978 and 1981 respectively. He joined Central Power Research Institution in 1982 and was working as joint director in high voltage division until July 2007. He completed his PhD from Indian Institute of Science during this year 1995. He has received the prestigious Bhaktas Medal for his PhD dissertation on pollution aging studies of insulators under DC voltage in 1995. Last year, he served as a professor and head of CPRI department in Sattagiri College of Engineering, Bangalore. He has retired from service during 2021. His areas of interest are design of external installation from the point of view of pollution of AC and DC voltages, pollution performance of DC insulators, lightning arrestor, and polymeric insulator. He has published more than 75 papers in national and international forums. He is also a senior member of IEEE and member in Institution of Engineers, India.
So, thank you one and all. At the outset, let me thank the organizer, HOD of the Police Department, faculty, and all of you for inviting me to give a guest lecture here. I am very happy to that. I request all of you to be seated too. They are all very fine students. We will not have any invigilation over them. They are very good. So I will start. See, this lecture, though it is slightly higher level, we need not worry. Final year students may be able to understand. Third year students try to understand that, absolutely no problem. But this lecture, though it is having some high technical issues, then and there I will explain you how researchers are involved in executing the work so that it will benefit the future. That is the first and foremost thing which I want to impart to you, so that you will involve in whatever the work you do, which will definitely yield results for the future.
The philosophy of IoT engineering, but actually the title had changed to pollution performance because philosophy means many of you may be afraid of. But whatever we do the work in your lab or whatever you try to involve and try to understand for the benefit of others is philosophy. Don't worry. So here I just want to explain you, because all of you are electrical. I just want to explain what is voltage, what is high voltage, what are the developments that take place in high voltage transmission, what is present trend in high voltage transmission, and new materials for insulator. Here only the pollution performance of insulator comes into play, and any other one. The definition of voltage is very, very simple. All of you must be knowing. But I don't want to ask question and make you embarrassed. But I will explain with the answer itself. The definition of voltage, as all of you know that, It is nothing but the work done on a unit positive charge or by a unit positive charge in keeping that at a particular place. Because if you have influence of charges, say positive charge, it will have a repulsion. So to keep that into that position from infinity, you have to do some work because you are holding it. Similarly, if you have a positive thing, it is okay. If you have a negative charge, if you want to keep it at a particular place, you have to hold it with certain force. If you leave it, it will migrate negative charges. So in both the cases, you require certain work done to it or by it, so that you have to hold at a particular point. The work done is nothing but that voltage. That is the definition. This you might be knowing only from field theory. I think you have field theory. Yes. Slowly they are going to remove it because they think it is the toughest thing, but understanding that is the best answer. So that is the voltage. Definition of that is the voltage. From that, high voltage has emerged, and then continuously the transmission level voltages, everything has emerged. Definition of high voltage is very simple. It is a relative term. For example, all of you might have worked in electronics lab, where the voltage will not be more than 5 volts or 12 volts. Whereas if you come to machines lab, you have to work with 210 volts, 400 volts. Okay. Then again, if you go to high voltage lab, you have to work with 50 kV, 100 kV like that. But for the transmission, it is very, very high. So for general public, we have to have certain definition that is high voltage, because public should be cautious that they should not touch into it. Therefore, we say high voltage. Any public places where the voltage is more than 1000 volts AC or 1500 volts AC have to be replicated with a figure so that it has to be kept as danger. So you might have seen that the skull and 2 holes will be kept, showing that high voltage danger. Okay. So for very high voltage engineers like us, 1000 volts, 1500 volts is not at all a voltage. But we have to be very careful. Knowing that, we have to be very careful. So why we have to be careful? Any voltage more than 100 volts, either AC or DC, is very, very dangerous. Why? Because it will give a shock. Shock means it will affect the nervous system. Okay, momentarily it will affect the nervous system and then on. But if it is attached with a current, say any current more than 5 amps and 100 volts, is more dangerous because it will result in very fatal things. If you have a low voltage, high current, you will have burns. If you have high voltage, low current, you will have a shock. If you have high voltage, high current, you will be flat, horizontal, you will not be able to stand up at it. That's a problem. So that's why we have to be very, very careful dealing with high voltages, more than 1000 volts and 1500 volts. So now power has to be transmitted from one place to another place because sources are at one end and sink is on the other end. And it is being separated by earlier hundreds of kilometers. Now you can say that it is separated by thousands of kilometers. And then you have to have transmission. So these transmission line voltages are different from general high voltage. So transmission line high voltage is normally earlier it was 11 kV, 22 kV. Now it is 33 kV and because anything more than 33 kV we say that it is a transmission line. Why? Because 11 kV is being used for distribution purposes. You can lead a cable and then you can distribute the power to the local areas. You can do it. And industrial supply is at 11 kV. Therefore, here 11 kV is coming under distribution for transmission of power over longer distances, 35 kV and above are being used. And then 110 kV level line have come, 220 kV level have come, and all those things were named as high voltage transmission. And the levels are 33 and 220. After After that, lines of 330 kV and above have come, and they have termed it as extra high voltage transmission, EHV transmission. Now you have in your era ultra high voltage transmission, because transmission lines have come more than 1000 kV line both in China and India. Therefore, these are the bifurcations of voltage levels. One is high voltage transmission, extra high voltage, ultra high voltage transmissions. And then in case of DC system, we say high voltage DC, 600 kV and below, and above 600 kV, it is termed as ultra high voltage DC. Even in DC transmissions also, we have good number of 500 kV transmission, but 800 kV UHVDC have come in India and in China also, and therefore any level more than 600 kV we say ultra high voltage DC. Hence in India we have UHVAC line, UHVDC line. That means there is lots and lots of job opportunities for the younger engineers until otherwise have to involve themselves in whatever they learn and execute in the operations executions. So why we have to go to higher transmission line? You might have studied transmission and distribution. Why? Because you can reduce the line losses. The moment the voltage levels are high, for the same power of transmission, current goes drastically down. Therefore, I square R will be less. Therefore, line losses are very less. The efficiency will improve because the moment the losses are low, the output voltage, output power will be high, and hence efficiency will be very high. Similarly, regulation is improved because receiving end voltage will be lower than sending it by very little amount. Therefore, regulation is good. Volume of conductor for the same power is lesser because current is going to come down. Transmission capacity will be very high because the product of PS and VR will be high. So, if you see the history of transmission line which has grown, starting from 1850 to 2000, these are the increment in the transmission voltage across the world. And India was lagging very much because during 1950s, when our country has taken independence, the transmission line and the other countries were around 310 kV, whereas we were having only 110 kV line. During 80s, when we started to work, the transmission line levels were 1200 kV in other countries, not transmission, research wise. But they were transmitting the power at 800 kV levels, but we were having only 400 kV. When we started to work, we had only 400 kV left. So this is the progress of high voltage in case of AC charge. But of late, around 2000, there are two countries in the world which is utilizing voltages more than 1000 kV. That is because China and India are the two countries that are competing each other to have higher transmission level. That is because when you have higher kV level, you can transmit bulk power over longer distances. India and China are the two countries where the networks are huge. You take any network, communication network or postal network or any other network is huge in case of India and China. Why? Because the population density is also high. In case of US, though the networks are high, population is less. They did not have to transmit as much power as India and China are doing. Therefore, India and China are the only two countries in the world by far higher voltage levels. So, in case of China, they have started using 1000 kV level during 2007 or so, and India also started more than this, 1200 kV transmission line over a distance of 2500 kilometers. The line is running from Vishwanath Charyali in the northeast region to Agra in the north of India. The line length is around 2500 kilometers and the power transmission is around 9 to 10 gigawatts. And next, huge power transmissions are still expected in India, and India is going to lead the power transmission demand throughout the world. So you can estimate what is the amount of power that can be transmitted over the distances here. If you are using 220 kV level, you can transmit around 100 megawatts over 100-200 kilometers, which are there during 50s and 60s. 330 kV level lines, India is having 400 kV level line, which can transmit the power around 400 to 500 megawatts over 500 kilometers. This is a period where we try to understand the power system. Now, the large thing is around 1000 kV is the transmission level. India has crossed it with 1200 kV level and gigawatts of power. Now we don't call the power supply in terms of megawatt, we call it as gigawatt, that is the power of 9. So we have to transmit around 5 to 10 gigawatts of power at 1200 kV level for the distances over 1000 kilometers. So India and China are the only countries that are doing this. So all other countries also have developed higher kV level lines. For example, Italy first, Russia, Japan, China and India. So these three countries are not using higher transmission line over larger distances. Though they have experimented in 1050, 1200 kV level line, they do not have higher transmission line for larger distances because they don't need the transmission line may be having lesser power transmission than India and China. So China has first started 1000 kV, highest system is 1100 kV, and then these are the values of withstand levels for them. And India is the next one which is leading now. Though Russia experimented for 1200 kV, India is having 1200 kV at a line or around 2500 kilometers. So this is the development. So we were lacking in power transmission by around 30 years during 1950s, 60s, 70s and 80s. Now we are the leaders. We are the courier for the world that we can transmit huge power over larger distances. Even in case of DC, we had 500 kV DC line over a period of time up to around 2000. China and India are having 800 kV DC line, and these things also, both the countries are having 800 kV HVDC line, and which can transmit power of around 5 to 10 gigawatts over distance of 2000 kilometers plus. See, if you have 800 kV DC, you can transmit around 9 gigawatts over 2800 kilometers to 1600 kilometers. That is such a huge amount of power can be transmitted through ultra high voltage DC or ultra high voltage AC. So even in distribution also, I think these values you just note it because as a power system engineer, you should know what is the amount of power that India is generating or throughout the world, how they are transmitting it up. General things you should know. So installed capacity is around 250, but now it's the old value. Now it has gone up to 385. The peak demand is also gone up to 210. We have transmission line 5 million circuit kilometers and beyond. We have 5 regional grids. And then national grid is under progress where all the grids are being connected, which will have a simple transmission. So that power can be drawn to these 5 regional things from the grid. So growth rate of energy is around 9% per annum, and now it is still increasing. these are the values of what is the percentage of the usage. Thermal usage of power is around 68%, hydro is 70%, nuclear is around 2%, and other sources is around 12.32. Where now they are tapping this with solar power and wind power, and this is going to increase by around 20%, and slightly the whole thing is being reduced because there are certain opposition for the usage of coal. Bioproducts are being left out to the atmosphere. They are trying to reduce this and increase the arguments. So these are how the electricity sector of India and how they are covered in a particular year. So the general usage is around share of renewable energy is around 17%, share of other fossil energy is around 18%. You can see in this map that coal availability is very high at the central portion, whereas hydro powers are very much available at northeast and northwest. So northeast you can get around 53 to 70 gigawatts nowadays, and here at northwest you can get again hydro power of around 23 to 35 gigawatts. So therefore, if you tap the power from here to our grid, okay, it is very good so that our energy capabilities will be improved. Not only that, it is very, very important because per capita living is based on energy consumption by a particular person. That has to increase, and therefore these powers, if it is connected to the grid, it is very, very good. So transmission lines, if you take DC lines, which is the latest one, if you go for AC, you have to go more than 1000 kV AC. If you want to go for DC, you have to go more than 500 kV DC. That is the trend. So in that respect, 500 kV DC lines which have been initiated during the 90s, these are the major lines. One is from Riyadh to Delhi, another is from Chandrapur to Padghe, another one is from Kolar to Talcher, another 2 lines of 500 kV have already come, and many more are there in the routes. So we have got a lot of lines which are coming up for DC and also for AC, and therefore huge amount of human resources are required for power sector. You are all lucky to be an expert and involved, but I cannot say that the money yielding may be more than the software sections, okay, information sections, but IT section. But it is a permanent one. It will never die. It will go on. There are lots of fluctuations in the IT sector, but there is no fluctuations in the electrical sector. So this is another way of representing our country progress. During 60s we have got 22 level lines. During 80s we have got 400 kV level lines, during which we started our career. Then HVDC back-to-back link has come during the 80s, and then 500 kV DC lines are started springing up in India from 1990 onwards. Then 800 kV transmission of AC have started from 2000. Now 1200 kV AC and 800 kV HVDC are the topmost transmission which are using bulk power of transmission over longer distances. So this is another way of representing how it has improved through the graph. The hydropower resources are located around 1000 to 2500 kilometers from the source, from the sea. It is convenient that we should have 800 kV HVDC, and India is going for large number of 800 kV. What is the benefit? You can transmit around 6 gigawatts to 8 gigawatts over 2000 kilometers. See, you might have seen that in one graph we have shown that, one slide we have shown that around 60 gigawatts of power is available from the northeast. To come to India center, the distance is around 2500 kilometers. Therefore, same point. In case of HVDC, they say the cost is huge. Yes, the cost is huge. But with the break-even point means where the distance is more than around 600 kilometers, the cost of DC will come down because of terminal cost of the equipment and transmission cost. So at that point, DC will be more cheaper. So we say that if you cross the break-even distance more than 600 kilometers, one can advise you to go for DC, HVDC. Therefore, for larger distances, you have to go for HVDC. It requires fewer conductors, no three-phase. Therefore, it requires fewer conductors. Power handling during the point is the major advantage of HVDC system because power handling during the point, in case of AC, is little difficult. But whereas in case of this, they will change the power angle, they will change the gate closing angles and can handle the power very easily during the point. And hence DC is power. So this is what I was telling. When it crosses 650 kilometers, okay, then DC becomes cheaper than AC, which is very evident. And when HVDC permits high power density when compared to AC line, then back-to-back installation is very, very helpful. In see, when you want to send power from one AC system to another AC system, you have to synchronize it. What is the point for the synchronization? Everybody get that? What is the point for the synchronization? Frequency. Phase. Voltage. These three are very, very important. If it's not matching, it's very difficult to synchronize. For example, if I want to synchronize from A to B, if A is having lower frequency, then the power will come from here and it will not go from here. So you control, then only you have to synchronize. So that's a very, very difficult task. Okay. In case of back-to-back stations, it is not required because you can connect any AC system to another AC system by conversion and inversion. So you can operate any particular station as a converting station. You can operate other stations inverting or reverse. So power transmission, direction of power transmission is very easy, can be controlled even though it is asynchronous AC systems through back-to-back. So number of back-to-back systems has grown in India. It's more than around 15 to 20 numbers as of now. And then major DC systems are that in India, at least 7 to 8 pilot kV system. And then one more UHVDC system is that. And then more number of pilot KVs are there on the cards. More number of HVDC lines are there on the cards. So this is another way of showing the map. That is Indian to Delhi. One more line has already come. Chandrapur to Kargil, and then Kolar to Lanche. And then one more national line of experimental. See, PHL of experimental with 100 kV transmission line DC. And then they went for 200 kV DC line. Finishing during 90s. But they learned what are the difficulties in DC transmission. They learned how to make the equipment for DC lines. And when they go for 500 kV line, they become the manufacturer and supplier for DC lines. So these are the number of DC lines. I will leave the PPT in the department side. They can refer to that. Let us see the requirement for HVDC line. I told you northeast to central part of India, the distance is around 2,900 kilometers. Initially they thought they want 2 HVAC line, 5 to 6 number of 800 kV DC, 400 kV 2 to 4 numbers they want. But it takes huge number of hours or years to go for this. Therefore, they are now going for 1200 kV. It's already been installed, and 800 kV has already been installed. They are going to have one more 1200 kV, and they want to have another 1 or 2 800 kV DC. So now, this is what the situation, present condition of our nation. But why we have to go for all these things? What is the philosophy with which we have to go for HV, extra high voltage, and ultra high voltage? See, first, what I want to say is the experience from the earlier transmission line or anyone for that matter will give you an input for the future. For example, when we had high voltage lines, there were lots of problems. Okay, lighting used to strike. When the lighting was striking, the equipment used to fail. When the equipment failed, we have to understand why it is failing. They brought the equipment for the laboratory and then cut it open and they try to understand where it has failed, why it has failed, how it is failing, and how I can improve over it. See, that is the involvement of many researchers. Go through the process of understanding it in a detailed way and understand and then move on is the thing or philosophy. See, further you have to understand the over-voltage, which is the main cause of the failure of electrical equipment. Types of over-voltage you have to understand. Origin we have to. The details like shape and the times have to be understood. What are the tolerances also we have to check it out. The effects of low voltage on the equipment are to thoroughly understand. And then protection for low voltage, so the costlier equipment will be protected. Which is the costlier equipment in the transmission system? Huh? No. Even if the answer is wrong, don't worry. Conductor. No. The costliest equipment is the generator itself. Generator itself because of moving part and the highest power. So generator is the costliest. Then comes the transformer. Then comes breaker, CPs, PTs. Finally the conductor. Okay. So when the costs are very high, I don't want to use it easily. Therefore, you have to protect the equipment for overloaders. These protections are made through surge arresters, which are placed at the entrance of the substation and at the individual generator, transformers, and others. We can categorize the overvoltage into two separate things. One is the transient and temporary overvoltage. In temporary overvoltage, what we have is the operating voltage, because the equipment has to operate for 50 or 20 years, whatever the lifespan of the equipment. What is the lifespan of the equipment of transformer? Transformer lifespan. This thing, generally you should know. It's around 25 years. It may come beyond also. It may fail before also. But generally a transformer should have a life of 20 years. Generator is costlier, therefore it should come at least for 15 years. Since the moving part is there, slightly become lesser, say around 30 years. Then insulators, just the insulator on the transmission line, either in the substation or in the transmission, it has to come for around 50 years. But if you process it properly and place it in the environment that you want to go, then it will come for 100%. Okay. Then any equipment in the transmission system should withstand lightning and switching impulse, which comes under transient definition. Transient overvoltages are nothing but lightning Lighting is the one which is from the ambient nature. We cannot do anything. And switching impulse is by the man-made. When you close or open the transmission line, there will be overload DC system. With that overload pitches, equipment should not fail. So we should try to understand what is the lighting impulse, which you must be knowing. Which is nothing but discharge the cloud onto the equipment or ground or transmission line or the conductor or any vessel. The discharge from the ambient cloud to the ground or to power system. Is it? For us, both together. See, if it hits directly on the pipe, there is effect. But if the pipe is very hot, then it will affect the electricity. Then if it hits the conductor directly, then direct impulses will go on to the sending end and receiving end, and all the equipment will be problem. And then if it hits the tower, then again huge amount of current will be going to the tower. The tower top potential will be high. There will be a backlash over from conductor to tower. So if it hits the ground nearby, not far, if it hits the nearby ground, then the coupling of the incident place unto the conductor, there is a capacitance which will pick up and induced voltage will be flowing on the transmission line. In all these cases, our power system transmission line gets affected and thus the equipment may fail. This is the earlier and foremost problem of the transmission system. There are discharges from ground to ground, which is of effect to our transmission system. Then intra-cloud discharge. The cloud will have positive and negative charges. So one of the clouds going below that will have positive to negative discharges. If the cloud itself is having very less distance between positive and negative centers, then you will have an inter-cloud discharge. Intra-cloud discharge. Between clouds, you have discharges because positive cloud can go near the negative cloud and there may be discharges. These two are not of that importance to the power system, whereas cloud to ground affects the power system. Here, what happens? Suppose the flight is going and the light is hitting the flight. If it is trapped in the intercloud, it's a danger. If it is passing through the cloud, it is having discharges. Then also it's okay. So these two comes for aviation, this comes for cost. This is an example of cloud discharge. Again, cloud to ground discharge. Cloud to ground discharge. Cloud to ground discharges. Sometimes 2 or 3 flashes will be occurring at a simultaneous point. Therefore, we say twin dances. This is a discharge by a cloud or NASA base. Just we can see the lightning may not be the shortest distance because this is a rocket launcher. Rocket launcher tip will be somewhere here, but you can see the discharges as taken a circular path around. Means they have got a diverter here, and they will take the safety that either the launcher or the launch pad should not affect. Therefore, they are diverting it. This is a picture which I have taken exclusively to show you that the lightning need not hit the shortest distance, it may hit a longer distance also. So, usually the discharges are negative, okay, and each discharge is a multiplied discharge. Suppose if you see a single lightning, the wink of eye, the lightning will be over. Within the wink of eye, the lightning is over. You can see only one flash. But if you analyze over a period through a voice camera, then you can see there are multiple discharges in a single flash. Means not only one discharge, lots of discharges, sometimes 100. So how it is done within a short time. Blink of the eye will take fraction of a second, millisecond, but this will happen in microsecond. So there will be hundreds of multiple strokes in one flash. And first strike is called a leader strike, and subsequent discharges are called dot leaders. This is what I was studying. First stroke will be high. You can see around 30 kilometers of discharge current is flowing. Subsequently it comes down, but it may have multiple discharges. So you can also see the current value of 30. Then again, sometimes few strokes. But anyhow, the first stroke is having the highest peak and fastest discharge also. So these are the results. Where I want to stress these points. These are the discharges where we have recorded through the fire towers, Eiffel Tower, and all the highest point. And they have the gadgets there below it. Whenever the strike comes, they are recorded it, and then with the records, they will analyze what is the stroke, what is the impulse, is it positive or negative, is it contains only one discharge, and how the rate of rise is going on, what is the peak quality, everything done. So, where I want to stress is they have worked day and night so that they wanted to send some information for the future human beings. So, these are the records which were taken during the voice camera. When you have a voice camera and use it for the lighting, you will get a streaks like this. Voice camera means which will have a film. Earlier, you might have seen that movies will have a film. Okay? Then they will roll it. They will say start. The wheels will be moving on and something. They will record the motion. Say they will say 10 feet, 10,000 feet, 5,000 feet, and then if they show you, you will have one complete action. One complete action will be taken two streams, and if you move it fast, you will get a motion picture. Therefore, it was told as a motion picture. But in case of lighting, when you want to study the lighting, the speed is much higher than the motion picture. Okay. It should be done with voice camera. In voice camera, you have got the film rolled at 30,000 feet per second. In 1 second, you will have 30,000 feet of film to be rolled. Okay. In that 30,000 feet of roll, if you roll it in that fast, you will get a right film. But if you roll it slowly, you will see the streaks where the initiation is from the cloud. The cloud discharge will start and it will complete at the ground or the tower. Then from the tower, return discharge. This completes one pulse. And when you convert it into a time scale, you can see the current will reach the peak, then it will fall. While the return stroke, it will fall. And this peak is around kgs, thousands of kgs in case of transmission line. For example, 400 kV line will have, suppose you have a general impulse, normal impulse, you will get around 1500 kV impulse. The peak will be around 1500 kV. And this 1500 kV will come within 1 microsecond. The rise time is 1 microsecond. Time is 50 minutes. You will get it in high voltage. High voltage power for minor wave fluids. Then you must be knowing about the lighting wave, impulse wave. The rise time is 1 microsecond, 1.2 microseconds. Time is 50 minutes. We used to say 1 by 50 microseconds. So that we represent the lighting. This is the one which we represent in the laboratory because they have researched so many times and they have come to the conclusion that if you do 1.2 by 50 microseconds generation in the laboratory, that is the one which will be applied to the equipment to check whether the equipment will withstand the lighting value. So if the equipment withstand that 1.2 by 50 microseconds in the laboratory, it can very easily withstand the cycle. So then subsequent are called the leaders. it is of not much importance to us, but the first wave is important, so that it is the one which is damaging them. Now, then, after understanding the ratio, they cut open the equipment and see, then they came to the conclusion that this will damage the 10% of the insulation in the transformers or any other thing. First 10%. Suppose the transformer is having the winding of around 1 meter. First 1/10 of 1 meter will have first 10 centimeters will have insulation damage. So if we strengthen that 1%, 10% of the winding, then that will not be for the thickness. So that is why we say whenever the equipment is being designed, that will take care of the overall things. So this is the first way. 1 microsecond, 1.2 microsecond is the peak, right? And then half of the maximum will be there up to 50 microseconds. Then 1.2 by 50 microseconds may be 50%. This we call it as front, this we call it as tail, which can be simulated in the laboratory by charging the capacitors in parallel and then discharging. When you discharge these capacitors to the load, say transformers, CPRIs, PPs or insulators, wave shape will be. There are certain tolerances, 20% on the wavefront, then 20% on the tail, 3% on the peak should have the correct voltage for the check. So when you have that tolerances, it is a valid impulse applied to the equipment. The equipment withstands the same, the equipment is good, you can use it for the transmission system. For the laboratory use, you should have an impulse generator, which is made up of number of capacitors, which will be charged parallel, discharging series. Similarly for the switching circuit, see, these voltages are important up to EHV level. So up to EHV level, the design of the equipment are going based only on the lighting performance of the equipment. So when they went for EHV level, what happened? The closing and opening of the line caused a lot of overall changes, and then the equipment used to be damaged. Why it is being damaged? Again, they analyzed. So these are the problems during 70s and 80s, and we were involved in understanding the switching circuits, how it affects the equipment, how it can be controlled, and how we can measure the variability, how we can execute at a site, everything we learned during our day. So that was the EHV. So then once you have understood, it has to be implemented as a transmission line. We implemented. Now we have moved to other things of ultra. Then what are the problems for ultra voltage? So these are some of the happenings for switching circuit, line closing, load rejection, switching of EHV reactors, fault initiation and clearing. All these are certain problems when it's a day-to-day operation. So all these will generate overload. For controlling it, you should have switching reactors. Otherwise, you should have closing resistance. When the breaker is being closed, you introduce certain resistance. Dampen it with the flow of current. And then short circuit the resistance so that it's not coming to heating. So hence, like that, they are controlling the switching circuit. Nowadays, it is being controlled by switching units. So out of all the things, closing and opening is a problem for switching circuit. So this can be studied through computer studies and then in the laboratories by RTDS. This is a new thing has come. If you visit the CPRI, they will be able to learn RTDS, how they are checking the transmission line performance. Real-time digital simulation is being conducted in the laboratory. They will simulate a particular transmission line parameters and study what are the overloadings, switching overloadings it will have, and then how it can be compacted, can be studied. these are the parameters: line length, then fitting network, and compensation, closing resistance, which is very important. Then trap charges, how much trap charges are there on the line, closing angle, and the pole span. So all the three spans of the breaker may not close simultaneously. There will be pole discrepancies. Then the span problem will come. So then for that line parameters you should understand. Sometimes corona also you have to understand. Corona will transfer the waveforms. Saturation. Transformer saturation is not reactor saturation. Remarks to the comparison of the field test of transient analyzer with computers. So now the transient network analyzer has changed to RTMS, real-time system simulation, where the computer is already attached to it. So the real-time regulator study will show you what are the overvoltage of a particular transmission system and how it is working. So these are some of the waveforms, how it has come. We have a switching impulse 250 by 2500. How it has come, there are a lot of work so that the peaks and other things are studied, where there is a dip on the performance of VT curves of the equipment, and from that they have become 250 by 2500. So this is the wave shape for the switching impulse, where the front is 250, tail is 2500 with the tolerances. So these are the incidences of switching set. One is recovery voltage out of fault clearing, fault initiation, low voltage in the line of fault clearing, energization of the long transmission line, low voltage in the line during and after the switching set. So these are some of the waveforms in the switching set, which is superimposed on the R frequency 50 Hz. So the switching impulse also can be generated with the same generator, but with different front resistance and tail. It is the same generator. The generator resistances will be changed. See, now any equipment has to withstand temporary overvoltages, that is continuous overvoltage for its lifetime, and high frequency overvoltages, and then it should withstand switching surge, and also it should withstand lightning. Now let me ask a simple question of when it is withstanding 6 per unit and above the lightning, why we have to go for testing switching impulse or temperature? We have to test other things, but why? If you are doing the test only with the lightning, it is sufficient. But why we have to test for switching impulse? You may not be able to get the answer, no, because I will tell the answer, you just go through. Any equipment, when you do the high voltage test in the laboratory, it behaves like a capacitance. It behaves like a capacitance. It is no more an inductor or no more it is like a parameter. It behaves like a capacitance in the high voltage lab. When it is behaved like a capacitance, it has got a frequency response. The frequency response of the capacitance may vary at any given frequency. It will peak at mid frequency or it will peak at higher frequencies. We don't know. So therefore, if the performance of the equipment should be there, it should perform at higher frequency. For lightning, if you just take 1 by 1 microsecond, it comes to megahertz. Megahertz. Again, at switching impulse, if you take 1 by 250 microsecond, you come to kilohertz. Megahertz, kilohertz, and hertz. So at these three frequencies, you are checking the high voltage. So it's a frequency one. And hence, if it withstands all the three voltages, it's a good equipment. So these are the voltages, impulse voltage and switching impulse voltage. and how much each system should be standard. Everything has been standardized. I will just take an example of water heating system where we have 1425 kV as sometimes we go for 1550 kV impulse, and for 400 kV we have 1425 as the switching impulse, and then for power frequency we have 630 kV as result. So again, these are the voltages for impulse and switching impulse voltages. This we know that lighting impulse can be generated from the impulse generator. Then again, switching impulse can be generated by the lighting impulse and also from the cascade transformer. And temporary overvoltage also can be generated from the transformer. But the problem for ultra high voltage is not lighting, not switching, but operating voltage. But the operating voltage is like the insulators may not be able to withstand. Why? Because it is nothing to do with the system, but ambient pollution is accumulating on the surface of insulator. Under wet conditions, it becomes conducting surface. When it becomes conducting surface, the current will be flowing on the surface. It causes A square or V2. When it causes A square or V2, dry band will be formed. The voltage across the dry band will be higher than the other voltages. When there will be R, we call it as partial R. They also call it as scintillation. The moment the scintillation is there on the surface, okay, number of scintillations will grow because dynamically the length of the creeping comes down. For example, the creeping is 1 meter. There is an arc of 10 mm, let's say. 1 meter, 1000 mm minus 10 mm. 990 mm will be the next creeping. So again, A square RT will be more. Some more scintillations will be there. At a given instant, there will be a lot of scintillations causing a flash, which happens at operating voltage. So here is a term. It doesn't affect any lighting or switching. So this is a problem beyond EHV. That is problem for disturbance. That is where our research went on. So we dealt with this problem in a thorough fashion and found that nothing we can do except the pollution is very severe and the insulator is not performing well. We have to change the material from mostly to polymer. The moment the invent of polymeric insulators come, things have drastically changed and EHV has evolved. From now onwards, you have to check what are the problems in EHV. And after understanding the problems, the solutions may lead to some other correct transaction. You understand how the research is going from its voltage to ultra high voltage. So these are the things what I told. The operating voltage, transients for the quads, normal power system quads, then impulse, switching impulse, and highest transient is in SS6 breakers. The flashover and all may happen because of fast transmission. So this is, you can say that 2 per unit is the withstand level of power frequency, 2 to 4 per unit is the withstand level of switching impulse, 4 to 6 and beyond is the withstand level of lighting. These are being streamlined for every system and they are mounted standard levels. So from now on, we just concentrate on the pictures, not on the other point. If you want the perspective of it, you can press. This is a figure of solid conductor. We call it as window conductor configuration. Conductor will come at the center of the window, then they make it flash over to the conductor again. So if there is a flash over here, then we have to keep the clearances such that it will not flash. Pollution problem is the important problem for the future of ultra voltage or later part of extra oil. The pollution will accumulate on the surface. When it gets wet in the average condition of fog during November, December, or light rain conditions in June, the current will flow on the surface, circulation will develop, number of circulation will cross and flash over, and operating voltage. So when the breaker will close, the condition remains same, again one more flash over. The auto enclosure will close 3 or 4 times, then permanently open. So if it happens, normally it will happen during early morning around 2 o'clock or something. And then at that time, you cannot control it where it has failed and how to clear it and all. Therefore, the study in a much thorough fashion and new materials of pollution, polymeric insulator have come and it is solving certain problems. But there are a lot of other problems also. So that pollution problem is the important one for the insulator. So it is not flashing or happening at lighting impulse or switching impulse, but it is happening only or so this I have already told. The pollution will be done when the pollution surface gets wet. The current will pass. A square or will open the dry band. Dry band will go across the line of the current and it will split the wet layers. Wet layers are split by the partial discharge. We call it as circulation. Number of circulations will occur on the surface. If it occurs simultaneously, then they die. So this is a definition of whatever I have said. So here, why these are all not a problem? Because it goes by the creepage distance. The creepage distances at HV level and EHV level also are higher. HV level is around 30 mm per kV, whereas at EHV level, say 220 kV level, it comes down to 20. At UHV level, you can see it comes to 50. Anything better than 20 is okay for us. It will withstand pollution of medium level. Okay, when the level of pollution even at UHV level it is light, then so therefore, unless you have a different material, you cannot solve the problems of UHV. The evolution of polymeric insulator is a tool, and therefore UHV has developed, and countries like India and China are going on. So this is the creepage length of any given insulator, the distance along the surface from HV to ground. So this is how the mm per kV creepage distance comes down to UHV. So the pollution level have been categorized into light, heavy, very heavy, and medium. Okay, depending upon the severity. The level of pollution for each level is light and medium. If you want it to withstand heavy, you should design the insulator properly, select the insulator properly, or you have to change the material. For heavy and very heavy pollution, if the insulator is giving a lot of problems, we tell them to change to polymer. So if it is very heavy and problem is that, definitely we say go for polymer. So test method I will not go into detail because you require 1 more hour for the definition of the test methods, how it is being conducted in the laboratory, what are the consequences of that, and how we can improve the withstand value of any given installation. It takes a lot of time, and just browsing you can just see. There are 2 methods, hard format, solid layer method, and we use to check the insulator with hard format, solid layer. So number of tests will be conducted on the insulator, but the problem is you should have patience in conducting these tests because each test is 1 hour and we have to conduct 4 1-hour tests after application of salt solution, pouring it onto the insulator, apply the voltage, wait for the flash overs, or if it is piston, and then you have to declare that whether the insulator is standing the particular salinity or not. If it withstands that particular salinity, again you have to go for another salinity and check at what maximum salinity it fails. Just below that, they say is that maximum withstand salinity. This maximum withstand salinity must be higher than the site CRT. If the site CRT is higher than the maximum withstand, it will fail in the salinity. So that's what it's like continuing process. To determine what maximum withstand salinity of an insulator requires around 4 days to 5 days test, continuous test. So you can see the arresters are being tested with the fog, which is sent on to it, and voltage is applied, and we have recorded all the leakage current, how it increases current. So the other method, solid layer method, we coat the insulator with a salted Ravi, dry it in the ambient condition, keep it in the laboratory, wet it with the help of steam fog, allow the current to flow on it, and check when it fails. But here the test duration is 100 minutes, that is 1 hour for one test. Like that we have to conduct 4 100 minute tests. These 4 100-minute tests we have to conduct at evening from 7 to 1 o'clock. So whenever it comes for solid layer test, you have to stay night, check it out, and to determine one maximum withstand salinity, it requires at least, because one day you can do only 2 tests on the sample. So when you do it for one withstand test, it requires around 2 to 3 days. For 4 to 5 withstand tests, it requires 15 to 20 days. A month is required for getting the maximum withstand salinity. And then you will check suppose number of samples are there, how to do that testing. There are patients for testing. So insulator is kept in the center after coating and drying, wet it with a steam fog, apply the voltage and keep it for 100 minutes. Either failure will come or it is done for other things. So how to come back? We can come back this pollution problem with a creepage extension. We can increase the creepage length of the insulator. Aerodynamic design as failed. Booster shed of polymeric material can be used. Increase the number of insulators can be done, and then greasing can be done, or resistive glazing on the polymeric insulator material. These are the problems which can solve the pollution problem temporarily. But permanent solution is a different material, the form of polymer. So methods of combating the problems are hard-line washing, RTV coating on polymeric insulator, performance, thickness we have to determine so that how best it performs on the site. So now we can see porcelain insulator we tried during pollution test or we have a when you go for polymer, it will have a very good hydrophobic property. It should not have a pollution problem. But the aging problem of this is a problem. So what are the aging problems? The material may yield up the organic conditions over a period of time. So the life of this polymer may be 7 years, 10 years, 15 years, 20 years. Whereas for insulator, the age is 50 years plus. So therefore, when it comes to aging, porcelain scores. When it comes to pollution performance, polymer. So to strike a diameter. So it is having a fiberglass rod supported by silicon rubber over it, and that end pins are metal. Porcelain glass, the pollution performance is not that much good, but the aging problem is very good. Whereas the polymetric material, pollution performance is very good, but aging is to be accepted. So, damages of post insulators are high, decapping, function, flash out, shattering, and all. That can be avoided in polymetric. Other advantages are that you can see the other advantages. Weight is very, very less, reduced breakage, okay, improved vandalism, even the gunshot also, if you strike it onto the porcelain, it will go to pieces. Whereas polymer will stay as it is, except a small hole. Then aesthetically it is more pleasing, improved resistance to vandalism, then improved handling of top floors. Mechanically it is very, very strong. Contamination performance is also very, very good. Therefore, in all respects, polymer scores for pollution performance. We say porcelain glass is hydrophilic, polymeric we say hydrophobic. That is the advantage for pollution performance. These are the polymeric. Now I will just put the pictures. Number of colors can be used. It is very easy to install. It is not tough as porcelain or glass. Easily practical if you have to study in the lab. Contact angle also is very important. You can see the water droplets are just like droplets on water streets. There are methods to find out the hydrophobicity of the surface of polymers. You can manufacture between these two. You can manufacture around 220 kg insulators, polymeric insulator. The area is surface suction. Whereas 20 to 30 times of this area is required for porcelain insulator. Aesthetically, it is very good. Colors are very, very choicy, and the shades also can be done. Therefore, it is easy to install it on lighting arresters, KTs, PTs, and any other. Wherever there are insulators, we can replace with polymer. Aesthetically, it will be very good. You can also have polymer housings. You can also have polymer canisters and breakers, vertical breakers, horizontal breakers. Colorful insulator aesthetically looking better, colorful insulators, which is very easy to install. Aesthetically, polymer canisters very thin and sleek. Hot coating can be employed on the station insulator, but it is very, very difficult to maintain. Every 7 years you are replacing with a new paint. This is what I want to stress. India struggled to get 1200 kV. They studied on a test plan for North India, where they went up to 1200 kV transmission, a check transmission of around 1 to 2 kilometers, and then based on the equipment and all indigenously made insulators, regulators, cylinders, buildings, transformers, everything indigenously made, and they are studied and they are implemented on 1200 kV AC line from Vishnacharya to national. So this is the study of window conductor configuration, flashover of window conductor configuration, 1200 kV single line substation, which is at we completed, the test have been completed during 2012 to 14. Single circuit line, 1200 kV switchyard, surge arrestor, These are the details of insulators. Support insulator, multiple arresters. Field testing have been done thoroughly, and they have implemented the equipment, placed it, checked their performance, and then finally they said, okay, we can have a transmission. Multiple arrester, we checked at CPRI, Hyderabad. 5 million volts impulse generator at Hyderabad CPRI. Not only you want to have the transmission line, you have to study its rate of way also. If you have a 1200 kV line, up to 100 meters on either side, no building should be there. You have to occupy the land to that length and to that length. You can see the dimensions of HVDC equipment. The people are just talking about near the converting transformer. This is the picture of the wall road. Massive wall road for HVDC. Mostly by Siemens. So transformer here, the horizontal breakers are being tested at CPRI. Arrested. Lighting arrestor will have introduction snap arrestor, inside the elements, the fiberglass, then silicon shielding. So this is the construction of lighting arresters. 7,000 capacity, 48 transformers, CVTs, power transformer, HVDC. See, nowadays, not only they have the power transmission, the data communication transmission also from one place to other. No doubt that you can transmit the data in air, high frequency. But still, higher data can be transmitted to power transmission conductor, provided the frequency is higher and it should not interfere with the power frequency. So, many people of transmission of the messages and data transmission, they use our power transmission line and use additional income for the power. Around 20% of the amount will be all in the data transfer from one place to another. See, this is a metal, the plastic film, coated, and then photographic coated film. So if you apply high voltage between Fe and Earth on the photographic plate, you will have designs through which you can study what are the polarity and what is the value. You can say whether it is positive or negative, what are its values. This is a preliminary one which they were using during 50s and 60s to measure the impulses. It leaves very good figure through which you can determine its performance. And also, so you can say what are the levels of voltages. And you can also say whether it is a positive or negative. And sometimes it is very good. See? So these are called Richenbach's figure. It depends on the photographic plate and also positive or negative. This is the impulse current, 80 kHz, direct wave, conductor configuration, the transmission line, horizontal breakers, lighting arresters. These are many equipments which are parallel transmission. Then installation will have first anti-entry will have a lighting arrestor and then the conductor. See, we are telling about the national grid, which is now of 400 kV AC. Slowly it will be converted to 800 kV AC, and then it may be having DC national grid. Okay? But each country they have their own national grid. It can be interconnected. That is what the Siemens have studied some times back. they told that it will take around 75 years so that the world grid can be adopted. When you adopt the world grid, there should not be any power failure. Grid failure should not happen at all. When you take all the precautionary measures, and are going to establish the world grid in your near future. So far it is a serious thing. Few pictures I will take only 5 minutes. Okay. Even if your lunch is being delayed, no problem. Okay. So IoT is IoT is not only a serious thing, it is also for fun. For example, you can have a discharge from reservoir. If you control the current of discharge, it will not happen anymore. It will be for fun. For example, in many movies you might have seen that people will walk through discharge. For that, discharges will be of low current, very high voltage, can be generated through Tesla car. You can touch 100 kV, 200 kV, no problem. But you should be sure that the current is in picoamps. If your current is very, very low, you can touch high voltage. But don't make it touch either rapidly because it's very high current. Even milliamperes is very high current. Your equipment is only milliamps, 10 milliamps, 15 milliamps, 100 milliamps. Okay? Don't try to touch it. But sure that it is having picoamps, you will have air basic test. Even a child can also touch high voltage. Provided current wise they can get. You need not touch, you can be just below the but take clearance from the conductor to yourself so that there should not be crossover. It can also be through the material, say perspex, on a longer run of impulses getting onto the perspex, it will give a design. And these designs of the perspex are being sold in for $5, $10. With colorful designs. Again, you can see that HV is here, RT is here, perspex is in between. And IoT is being applied continuously means number of pulses per day. After a long time, these discharges will travel through the perspex to give that. These are corona discharges of the damper rings. See, it is not only the material. You can also protect your costliest car through Tesla coil, where continuous discharges may go around the car so that the thief will not come and kill your car. You can protect your car by Tesla discharge. And you can be safe inside the car. Should not come out. You switch off and then come out. Thus, if it is a costless car, you can protect your car through Tesla discharge. So these things I wanted to show you because IoT is a serious subject, the same category. Understand it properly. If you know the safety of it, can be what it costs. If you have any question, you can ask. I know there will be no question, but at the same time, I will leave it to you. If you have any question, you can inform your HOD or any process of electrical. Thank you very much. Thank you for your patience hearing. I would say thank the organizer for giving me an opportunity to talk to the students. But I will tell one thing, whatever you do, wherever you are doing the work or something, involve yourself deeply, take out something for the future. Thank you.
Thank you, sir, for your immense knowledge and experience in sharing it. And I request Ms. Sanchita to come and read both of her times. applause. We thank you, sir, for accepting our invitation in your busy schedule and sharing the immense knowledge in the field of pollution performance of insulators. I would like to express our sincere gratitude to our honorable chairman of the Oxford Educational Institution and president of Children Education Society for his motivation and support. I would like to thank our principal, Dr. N. Kannan, and deans for their constant support and guidance. I also wish to extend our gratitude to our HOD, Dr. B.S. Bharat sir, for providing his valuable suggestion, encouragement, motivation, and support. A very special thank to organizing committee and to all the faculty members and students of the department for their continuous efforts and work for the smooth conduction of the workshop. We are happy to express our heartfelt thanks to all the active participants on this event being with us throughout the session, and I am sure everyone would have gained very good knowledge regarding the topic of this guest lecture. Thank you.